The problem that we'll do next is called as gambler's rule. So what is this problem? So there are two gamblers. There is a gambler A and there is a gambler B. Okay. So what they are doing is, this gambler A has, let's suppose, some I dollars, and this gambler B has n minus I dollars. Total they have n dollars. Okay. But in total they have n dollars and n rupees. So they are playing some gambling game. So whenever one wins, okay, let's suppose this person wins with probability P and this person wins with probability 1 minus P. Let's call it Q. Each round. So there are games, some game is happening. So the winning probability of A winning that round is P, and winning probability of B is 1 minus P. Okay, so this is the set of the game. Two gamblers, A and B. One has I and other has n minus I dollars. And probability of winning of A for the one round is P, and probability of winning of a round for B is 1 minus P. Okay, or we will call it Q. Now you will have, they keep on playing this game. And each time, if let's suppose A or B wins, they'll give $1 or 1 rupees to the other person. So if A wins, A will get $1. If B wins, B will get $1. Okay, and they'll have to give it. So in total, the system, if you see the system, total dollars before and after will remain the same, but the money will get transferred. Either A will win the whole, and they keep on winning it till one of them goes bankrupt. That's why this is the ruin is there. So till one of them ruins him or herself. Okay, so it goes like this. So you have initially some dollars, some I dollar over here. Let's suppose A is having I dollar, A is having I dollars, and B is having n minus I. And let's see A is over here. If A has I dollar, something of this sort. So A can either go right, he'll win $1 plus 1, or minus 1, he'll lose $1. So at the end, either A has to lose everything to go bankrupt, that is, he has to lose everything, that is, go to $0, or he has to win everything that B has, so as to reach n dollars. Okay, so these two are called as absorbing states. The 0, n are called as absorbing states. Absorbing states. Because here the game will stop. They keep on doing this. They keep on doing this. Either the first person wins, or the second, or A wins or B wins, until one of them is bankrupt, or and other one wins all the things. Then we stop the game. So you have to compute probability of A winning, or symmetrically probability of B winning. You have to compute this. I made it more generic. So usually this P and Q are this P and this Q are given as half probability. Okay, we'll do that case as well, but I'm making it generic so that when P and Q is not equal. Okay, I'm making it generic. So we have to compute probability of A winning. First, before solving this question, why is it used? If you see, this is also used as a random walk. You can think of like at a random walk. If somebody, a drunk guy who is walking, so he's here. So we have to see either if he reaches destination 0 or destination n. So he takes one step over here, sometimes takes step back, takes step here, takes step back. So what is the probability he'll keep on doing to and fro, or he'll reach one of the absorbing states? He'll either reach n or he'll either reach 0, something of this sort. Okay, and this random walk has a lot of application. I'll repeat probably once more so that everybody is on the same page. So we have two gamblers, gambler A and gambler B. So gambler A has I dollars and gambler B has n minus I dollars. And in total they have n dollars. They play some game. They can play a flip of coin, they can play dice roll, and they play it in multiple rounds. They play round 1, round 2, round 3, something like this. The probability of A winning a round is P. The probability of B winning a round is 1 minus P. That is, we can call it Q. So I am saying that there are two absorbing states, the 0 and this n. That means either one should, let's suppose if A has to win all the dollars, then game will stop. Or A has to lose all the dollars. Either A has to go to the 0 or to n, to these absorbing states, in order to stop the game. And now in each of the round, whoever wins the round, he gives the $1, he gets the $1. If A wins the dollar, if A wins the round, A gets $1. If B wins the round, B gets $1. At the end, the system will still have the same amount of money as it initially had. So you have to compute probability of A winning or probability of B winning, one among them. And I made this problem more generic. Usually, if you see in the textbooks, the problem given is that P is equal to Q. They are saying that they flip a coin, and the probability is 1/2 and 1/2. And what's the probability that A will win? So what I can do is I can make it a recursive equation. If you see, I can solve it through recursion. Solve it through recursion. So here I assume that people have a computer science, they know how to solve recursive equations, but it's a very wild claim, and I anyway go with that. So what I'm saying is, I'm saying Pi is the probability that because we have I dollars, so Pi is the probability that will get A will win. So let's suppose Pi is the probability that A will, because he has I dollars, we'll say that Pi is the probability. Now what you have to see is you are at this position. Let's suppose this A is at this position. Either he'll win a $1 with probability P, or he'll lose $1 with probability 1 minus P or Q. So how I can write is, he'll either get Pi. Pi will either get Pi plus 1 or Pi minus 1 in each round. He'll either win $1 and go to Pi plus 1, or he'll go to Pi minus 1, if you see it like this. Okay. So what's the probability that he'll win these many dollars? He'll win, that is, he has probability P. I'll write it like this, P. I'll write it like this. So Pi is P and with this is Q. Okay, so I made a recursive equation. Okay, so Pi is equal to probability that is he'll win, and he'll move to Pi plus 1 because he's at Pi. He has to move because we have to find Pn. He gets all the dollars. The probability A will win when he has I dollars. So that's what I said. Probability A will win because we assume that A has I dollars. So when he has I dollars, this is the probability. So if he has I plus 1, the probability will obviously change. That's the Muzaffar's argument, because if you have more money, so you should at least have higher chance of winning then. Okay, because let's suppose if you have total $50, if you already have $49, you have to just win one round to win all the money. Okay? So having more money should be proportional. That if you have more money, the chance of winning should be high. That's what I'm saying. If you have Pi, that is A will win. That is a person with I money will win. So he'll either move in each step. He'll either move to I plus 1. He'll move one step because he'll earn $1. But what's the probability of that? That is probability is P. Or he'll lose with Q probability and he'll move to I minus 1. Okay, this is the equation. We call these difference equations. You might have heard about differential calculus. So this difference equations, they're not taught much. Okay, so but somehow they follow almost many of the rules which are followed by the differential equation. But we'll anyway solve this. So this is the recursive equation that we have over here, and then we have boundary conditions. So boundary conditions is P0. P0 basically means he has nothing. So what's the probability of winning? 0 then, because he got nothing. I means I dollars. When he has $0, probability of winning is 0 because he lost. Probability N, P of N is 1 because he has got all the dollars. That probability of winning is 1 then. If he is at P of N, if he won all the dollars that we had on the table. Okay, these are called as boundary conditions. Okay, so these are the two conditions. Initially we made a equation and then we also wrote the boundary condition for this. So in order to solve this equation, you might have also done if somebody has done differential equation course, so there you initially guess and then you check it and then you find a generic solution. So we do the same. So what we'll do is we'll say, let's suppose Pi is equal to Xi. Okay, and we'll try to solve it with this and then find the roots of this equation, and from the roots we'll try to find a generalized solution to this. Okay, and this is the step which I was hoping that you directly will not understand, because for this you'll have to understand all the things about difference equations, how to solve them. But for the sake of assumption here, I'll assume that you can either believe on me, this is how we solve difference equations, or you can go and read about difference equations. So this is Pi is equal to Xi. So I'll put directly over here. So this will be equal to like this. Xi is equal to x to the power I. This is P to the power Xi plus Q to the power. This is Xi plus 1. This is Qxi minus 1. What I did. Okay. So I could have done it on 0. So this 0 won't give me a good case. So I'll put I is equal to 1. So if I put I is equal to 1, this equation, okay, I could have done the boundary condition, but I'll use boundary conditions later. So this will be x square is equal to P. This will be x1, x square plus Q, because this will become 0. Anything raised for 0 is 1. So the equation now becomes Px square minus x plus Q is equal to 0, something of this sort. I have now a quadratic. You are seeing that how calculations can get tedious. Okay, keep a check on the calculations if I am making some wrong calculation. Px square minus x plus. Now I'll solve the roots for this. Okay, so how can I solve? Quadratic formula. X is equal to minus b plus minus under root of b square minus 4ac. So what I can do is x square minus b. So this is 1. This is minus and minus 1. This is 1 plus minus under root of b square. Okay, so what is the b square? So b square again is 1 minus 4ac. Minus 4ac. A is this and c is this. So p and q. P divided by 2a divided by 2p. This is a and these are the roots. So now if you solve these roots, if you solve for this roots, x will either be equal to 1 or x will be q by p. Okay, how to solve this? So you just have to subtract this. You can write it in certain way so that this gets cancelled. Here I am again skipping a step, assuming that once you go through the recording you will reason it. It's not very difficult to come up with this, so I am saying that this thing can be expanded in a minus b whole square. Okay, because you can clearly see that it has 1, it has 2 and multiply by 2 square, you can do that and you will reach two conclusions. You will reach x is equal to 1 and you will reach q by p. So by now you should be well versed with quadratic formula, using quadratic formula. Now in order to have these two squares, so how to solve the difference equation now? Now you take this linear combination of these two roots. So this pi is a to the a multiplied by first root plus p second root. So this is how we solve the generalized solve. So what we did is initially we substituted this. This is the way how do we solve these difference equations. The first thing was I substituted something and I substituted x is equal to 1. Okay, this is for a particular instance. This is for particular one instance I did it, and I came up with the roots for that in order to solve it in generic. So how do we do it now? So in order to form the generalized thing, we take a linear combination. We take a linear combination of the roots of the equation. Now I said this a is some coefficient, this b is some coefficient. Here I'll put the roots. This pi is equal to a multiplied by x. The first root is 1 to the power I plus p. Second root is q by p to the power I. Okay, this is how we solve these difference equations. So you initially make a guess, and from the guess you take a root, and then you take the linear combination of these two roots. So this pi can be now written as a plus, because 1 to the power I is 1, doesn't make sense. This I can just write it 1. So b q by p to the power I. So now I can use boundary conditions to find the values of a and b. Okay, and then substitute back. So what is the boundary condition? The first boundary condition is p of 0 is equal to 0, and the second boundary condition is p of n is equal to 1. I can use it here over here. So p of 0 is 0, so I can put 0 is equal to, so p of 0, that is this, p of 0 is equal to 0. Then a to the power 1, this is a plus b. So now you see this b, and this I is as 0, so anything raised to power 0 is 1, so this is a plus b. So from the first boundary condition, we employed that a is equal to minus b. This is what we got. Okay, substituting the first boundary condition in this, so we got a is equal to minus b, and accordingly we'll put the second boundary condition, p of n is equal to 1. So we'll have to put p of n. So p of n is equal to 1 in this side, so we'll say 1 is equal to a plus p into q by p by q or q by p, q by p to the power n. Okay, and now from here you can substitute the value of b as minus a, so you can say 1 is equal to a minus a, because b is equal to a is equal to minus b, or b is equal to minus a, so that I'll take one of the things common. Okay, so this is a q by p to the power n. Then I'll take 1 is equal to a, take it common, 1 minus q by p to the power n. Here I'll compute the value of a. A comes out to be 1 divided by 1 minus q by p to the power n. Okay, from the algebra. Okay, might look pretty tedious, but this is the standard procedure that we have to go through. Okay, now you saw this. You saw the two cases now. If you see these two things, you saw this a, we got this value of a, and we got this value of a, and we substituted these values. So now in order to compute this, so here pi, when I substitute these a and b in pi, so because pi is a plus whatever here the equation was, so here pi a is equal to this and this. Now I found the values to a and b, so now you can substitute these values. You can come up with this pi is equal to 1 minus q by p to the power I divided by 1 minus q by p to the power n. What you will come up with by substituting the values. So you have computed the probability of a winning. So this is when p is not equal to q. Okay, when p is not equal to q, I made a generalized claim. If p is equal to q, let's suppose, if p is equal to q, so I'll solve it by limits. I can solve it by limits. So then pi will come out to be I divided by n. Okay, how can I solve it? Solve it by limits. Okay, this is in the limits property. This is like 1 minus x divided by 1 minus x to the power n. So I have to just write it and you will see that it once you solve the limit, it will come out to be I minus. So why am I leaving the calculations? Why am I not showing you all the calculation, all the mathematics done? The first thing is because I don't assume that you have all the requisites, or if somebody has to fill these gaps. And the second part is calculations are not important. Okay, that's why people directly give this answer to the gambler's rune. Okay, because I want to make some claims out of this. So this is the probability when P is equal to Q. Probability P is equal to Q, and this is when P is not equal to Q. Usually you will see this case done in the textbooks, and there is a huge proof. Okay, and here I did a lot of jumps. The first jump I did is I made a diff till here. I think it was pretty clear. I made a difference equation till here. Okay, and after this, how to solve the difference equation. So this is where the new mathematics kicked in, but it was irrelevant to you. Okay, even you should not bother. If you don't understand whole of the thing, you should not be bothered at all. The only thing that you should be bothered about is the result. Is this result over here, or this result when P is not equal to Q, and when this. These were the two results we had that were of our interest. So if we now focus on this result more, let's say we'll focus on this. So what is the implication of this result? So I said the key observation over here is this Pi is directly proportional to this I. So the more money you start with, the more likely you are to win. Okay? The more money you start with, the more likely you are to win. Okay, so if you are doing any gambling game and assuming that there are two gamblers and they have equal probability, so even the person who has more money, so it is very high likely that the person will win. This goes with the casinos and the gamblers. So when people go to casinos, because in general casinos have more money. Okay, so probability is towards more towards them. So similarly, so this goes, I write it here. So when we have casinos and gamblers, okay, these people have advantage. Casino people have advantage. Similarly, when you do trading, so trading in that big institutions has an advantage. So it is not recommended for an individual to do the trading. Why? Because they have less capital as compared to these big institutions. So in comparison with these big institutes, they have very less money. So it is better for a trader to invest, not to. It is better for a person to invest, not to trade. So if they are somehow like people are doing forex trading, or they are doing FNO, so it is bound that by probability won't support them. So in the longer run, they lose a lot of money. Okay, so that is evident from this equation. Pi is equal to I by n, and given that I am making a assumption that I and this P is equal to Q, that probability of winning for both the parties is same. So here, if you can see, so casinos, I am assuming that casino has the similar winning rate as winning probability as that of the person who is gambling there. Okay. So now let's suppose let's make some assumptions. Let's just tweak this probability. So we're assuming that P is equal to Q. Let's tweak it a bit. So we'll say, let's suppose P is equal to 0.9, 0.49. We'll give a little bit advantage to Q, little bit advantage to the other player. Okay, and then we'll see how does the money impact. So I'll show you some of them. We won't compute it directly. I'll just show you some observations that I have written here. So now if you have $20 in total, okay, if you have $20 in total, so the probability of winning, but the other person has very less advantage. Q basically here is 0.51. So if you see the difference between these two it's very minute. So if you start with total money, that's n is equal to $20. I and n minus I. So here we have these $20. Then the probability of winning goes to 0.4. Okay, with $20, probability is 0.4. Still, it looks quite decent. So if you go a little bit higher money, if you go to $100, okay, if you see this $100, the probability goes to 0.12. So now if you see $200, the probability goes to 0.02. Okay, so if total money, if you increase this money, if you increase the money, and then you will see this probability even giving a slightest advantage to the other person, the probability of the person which has less advantage decreases drastically. Okay, that's what people usually do. So this shows even smallest bias can directly reduce A's winning probability. Okay, if you have a slightest bias in here, and you know how casinos and in these gambling games work, they have huge bias, and then you can clearly see that the people are bound to sort of lose there, and because this probability will even go down to 0.01, 0.001 sometimes. Okay. And one more thing that, one more question that I left with you is, I told there are two states. One is absorb zero state and one is nth state. These two were called as absorbing states. So they were called as absorbing states. Why absorbing states? Because the game will stop there. Okay, if we had player and it had I dollars, so either it will move right or it will move left based on whether it will win a dollar or lose a dollar. So if it is winning a dollar, it will move to the right, I plus 1, or if it loses a dollar, it will move towards the left, that is I minus $1. So I said, is there a possibility that they'll never reach an absorbing state? It will always happen that sometimes it will go there and then come back, and the game will keep on going. So basically it will not reach any absorbing state, but rather just keep on fluctuating, keep on doing this to and fro motion. Okay, just go right and then couple of steps left and couple of steps right. Okay, we'll see this mathematically. Is this possible mathematically? So if you see, winning probability of pi is equal I divided by n. So if I say what's the winning probability of b, then because b has n minus I money, so if you see, this is probability of a is winning. So what's the probability that b will win? So that will be n minus I divided by n, because initially a had I dollars, so the probability of winning was I divided by n. Now by symmetry I can do it same for the person b. Person b had n minus I dollars, so just substituting this I by n minus I, so this is the probability of b is winning, the probability n minus I. Okay, so now if I add these two things, I minus n plus n minus I divided by n. Oops. So if you see this, so this will come out to be 1. Okay, that means this basically means either other one will win the game, either a will win or b will win. So statistically or probabilistically, it is not possible that this scenario will happen, that is no absorbing state will be reached because of this result, because we can clearly see over here probability of winning of a is this much and probability of winning of b is this much. So when you add these two probabilities together, it comes out to be 1. Okay, if it came out to be less than 1, okay, then we would have thought, okay, there is still a possibility that this game will run forever, there will be this fluctuating behavior in the game. But clearly you can see over here that when you add these two probabilities, it comes out to be 1. So this leaves us with no possibility that this thing can happen. Okay, so these were some of the observations that we saw from the game, and this is quite a famous problem, and you have different versions of this game. So now there are different advanced versions of the game. You can do the same analysis on the game and you can come to the conclusions. Any questions or gamblers rune? So I'll write some of the applications of this problem. And here, before going to the application, I'll make a comment. So whenever you read something, so whenever you try to let's suppose understand something which is of really importance or historically which has stood out or which has been quoted in many books, the first thing that you should think is, how can I use the same template and how can I apply this to the other problems of different domains? Okay, so there is a high possibility that whatever you are seeing that is repeatedly used by many books or it has been discussed a lot, so it means that it has a lot of applications in other domains as well. Similarly, this gambler's rune has a lot of applications, not just in gambling, maybe in some other domains of life as well. The initial application that I told you was from this stock market and investments. Okay, now you should keep your eyes open, whatever problem we have done or whatever notion we have developed for probability. So keep your eyes open that in real world, is there some problem which fits the description, which fits whatever I have learned so far. So because that's a skill. So if you know something and if you can generalize it to different domains and different problems, then you don't need to reinvent the wheel again, because you have developed these notions for the other things. And if you saw some similarity, if you saw these analogies, if you saw, okay, these things go hand in hand, they go in parallel, so can I use the same thing that I developed for this into this as well? So I said we just analyze the gambler's rune. So you can do the same analysis on this stock market, where an investor repeatedly trades stocks which has limited capital, okay, and if they go bankrupt or not. So you can see this. And the second application is in genetics. So if you people are interested in genetics, so you might have heard that genetics is the field where we study and genes, and I'm just vaguely defining it. So we study genes, and in that we see, okay, this gene is dominant, there is a recessive gene. I won't go into details, but I assume this basic knowledge you have. So in that, there are two types of genes. One is called as dominant gene, and we have recessive genes. Okay, dominant basically means if in an hybrid position, so this dominant gene will express, basically show its effects, and recessive gene usually does not show effects. So recessive gene only shows effect if it is present in pure homogeny. That means if you have, let's suppose, dominant gene is A, okay, and its recessive gene is A, small a. So if let's suppose you have A and some, let's suppose, some small a, so here this will express, this A, capital A will express. So if you have this A and A, still this A will express. Now if you have A and A, then only there is a possibility that this gene will express. Okay, so in genetics, the application of this Gamblers' ruin is, let's suppose in evolutionary biology you have two competing traits. Okay, there's a genetic trait, let's suppose color of eyes. Let's suppose we consider it blue and let's say brown. So now these are two genetic traits which compete with each other based on the genotype and stuff like that. Okay, and now which of the traits will be shown in the population. So it depends on it somehow is like that Gamblers' ruin. It somehow is like that these things are competing together. Okay, because you can see that population is still growing and these two traits are competing together, and now you will have to assume that in general, let's suppose after 100 years, after 200 years, or in general in the span of this universe, what will happen, which gene will dominate. Okay, so a trait can get fixed or it can get extinct. It can either get fixed or can get extinct. That means it can go into one of the absorbing states. It can either go to 0 or it can go to n. Okay, because they have some probability, some probability of winning, some probability expressing themselves. Okay, if they express more, that is they are winning these dollars. So if they keep on expressing, so then that means there is a very high chance that that gene will win if they keep on expressing. That means they keep on winning. So sometimes they call it genetic lottery. Okay, genetic lottery basically means this. So if some good genes came to a person because of the genetics, so he won the genetic lottery. Okay, so everything is also probabilistic there. So in this case, if there is a trait which starts with this probability I, let's suppose, okay, it starts with I, and I basically means number of people here. It started with these many number of people. So we can say it started with 20% of the population of the world. And then if it kept on, once more children were born, and it kept on dominating, it kept on showing its effects, it kept on replicating itself. That means it is always winning that game. So it will go into one of the absorbs. So if it keeps on winning, so it will go on this end, and that means it will spread in the whole population. Or if it kept on losing, so what will happen is it will reach to 0, it will get extinct. So there will be some facial feature, there will be some features in humans which got extinct because of this, because of the genetics, or there will be some things which got dominant or which are now prevalent in 100% population because of this. Okay, so here you can clearly see that why this Gamblers' ruin also makes sense in genetics. Okay, then similarly you can see a lot of courses of life, a lot of domains in which this Gamblers' ruin can be fitted, and these things go in parallel, and you can clearly make analogies. Okay, this problem looks like Gamblers' ruin, so can I formulate the problem into Gamblers' ruin, and can I use the same conclusion that I made there? Probability also is used in genetics. Okay, and mathematics is also used in biology, because there is a notion that biology people do not use mathematics per se, because you will see that mathematics doesn't require biology. Okay, if you have mathematics, it does not require biology, but it can explain because mathematics doesn't require any subject either. You just have a phenomenon, you abstract out the details. Once you abstract out those details, and you can fit into different domains of life. Okay, as we saw Gamblers' ruin problem. It is a template of a problem. Otherwise, I could have just made this problem. I could have done one more level of abstraction. Even do not name it Gamblers' ruin. Just have a generic setup. After generic setup, I'll reach to the conclusion, and I can use this setup to different domains, as I used it in genetics, as I used it in finance and stuff like that. So here I'll sort of suggest, if some people are reading biology online, if they are doctors, do recommend them to read about stats and probability. Okay, if they have to only master one topic in mathematics, so they should do probability and statistics. Okay, so if you have to recommend to your doctor friend or the people who are in your family, they want to become doctors, and the only subject if they want to master in mathematics, it should be this probability and stats, because it is used everywhere in biology. Okay, in genetics, if you see, I just showed you one example. The whole of the genetics, which when it was discovered, it is based on probability. So if you see there, if you see that there are two genes, okay, two genes are independent. So what is the meaning of independence? That one is not affecting the other. Okay, there's a concept of independence that we have seen. Okay, so my suggestion for you people is that if you have any person who is taking biology and who is becoming a biology major, tell them to master this probability stats. And why am I telling you this? Because someday I'll have to cure myself. I'll have to go to a doctor. If the doctor doesn't know probability stats, and I'll say big no, I won't go to you because my life is in your hands. Or if somehow you didn't know probability and stats, if you took wrong decision because of that, so I am basically tossing my life there. Any questions on this? Okay, let's move on to the next topic. So what I said is, I told you once we read about probability, so there are a lot of confusion that people had. So we saw Salic case in which the posterior was confused with likelihood, and we also saw that sometimes people confuse posterior with the prior. So we saw all of these confusions. So one more confusion that we saw in the class itself was people confuse between mutually exclusive events and independent events. Okay. Let's now see why this confusion arises and how can we how should we not think about these things so that we don't get trapped in this confusion. Okay, so if you see this mutually exclusive, they're called disjoint events. So we have disjoint events, something of this sort. If I make a Venn diagram, so we have an event A, so we have other event B, something of this sort. Okay. So I am saying that these two things are mutually exclusive if they have nothing in common, if there is no intersection between these two things. There is probability of A intersection B is 0 because there is no element they have in common. Okay, probability of both of these happening together is nothing. Okay, now if you think it in terms of independent, in terms of dependency or independency, so how can you think about that? So what I said is, I said if there are two events, we have event A and we have event B. If an event happened, if let's suppose this event A happened, okay, if it gave no information, about B, okay, that means if one event happened, it did not give me any sort of information so that I can update my belief about B, then I call these events as independent events. So if I now see these two events, A and B events, so I said there is no overlap between these two, they are disjoint events. So if let's suppose somebody told me that this event A happened, so can't I say that B will not happen? Because I know that these A and B are disjoint, they are mutually exclusive. If one thing happens, other thing will not happen at all. Okay, this is something like this. In genetics, having blue eyes and brown eyes is mutually exclusive. Okay, majority of the times. So there are cases where one eye is blue and one eye is brown. Just remove those cases. So if you see these two genes, if they are determined by genetic factors, so these two genes then will be mutually exclusive. Either one will express or other will express. Both can't express at the same time. Okay, so that is what is happening over here. So if there are events which are mutually exclusive events, that is the probability of the intersection is nothing. That means they cannot happen simultaneously. So they are very much dependent. These things are then dependent. Why are they dependent? Because if A happened, I am sure that B will not happen. So happening of A gives me an additional information about B that it will not happen in any case. Why? Because they are mutually exclusive. So we should not confuse between independent events and mutually exclusive events. Okay. So how can I think like let's suppose how can I think like these mutually how can I see, how can I visualize these things? So let's consider this. Let event A is rolling off a die, rolling off when you roll a die and you get 2. So let's suppose event E is getting a 2 on the roll, getting 2 on a dice roll. Let's suppose F is an event getting 5 on a dice roll. If you see both of these events, they have nothing in common. Okay, and they're dependent. Why are they dependent? They are mutually exclusive and dependent. So if I am saying then getting 2 on dice, so if I got 2 on dice, so it makes sure that I'll not get 5. Okay, because I got 2 on the dice. Okay, and if somebody says what is the probability of 5 happening now, so given that 2 happened on the dice, so there is 0 probability that 5 will happen. So I consider this as an event, this is an event. So these two events are mutually exclusive events, but they are very much dependent events. Okay, so what are the independent events then? So independent events are the events where happening of one gives me no additional information. It should not give me any additional information. So let's suppose if I am saying I have an event E, which is flip of a coin. Okay, and then W, weather outside. If I flip a coin, let's suppose I got head. So does this head tell me anything about weather outside? No, it does not. If somebody told me that head happened or tail happened, my probability of what is weather outside does not change. So basically this evidence is irrelevant to the process that I am doing. So I am observing weather and somebody is telling me that something happened which is irrelevant to this. Head came out to be, there is head, or Mahmoud fell sick, God forbid, something of this sort, which is totally irrelevant information to this. Then I'll call these two things as independent events. Okay, so in which one event, happening of one event does not give me any information about the other event. Okay, so these things will be called as independent events. So that's what I claimed. Are disjoint events then independent? No, they are very much dependent. Why? Because happening of one event tells me short the other event will not happen. Why? Because they're disjoint. Okay, I hope that you got this. Somehow you should remove this confusion, because they're two different things. Okay, one more comment that I like to make over here is, usually when do we see independence or dependence? When do we see independence in events? So when do we see these two events are independent? So if in the two events, if the generating phenomenon is different, if the generating process is different, in general, when you see an event, it is generated by something. So if the generating phenomenon is totally different, then there is a high chance that these two events will be different. Okay, this will also apply to the machine learning. So when you see that there is a feature, okay, when you take one feature, if you have to see that if other features depend or independent on other feature, let's suppose you have feature f1 and you have feature f2, you have these two features, the f1 feature, f2 feature, because usually you will do feature engineering in a lot of tasks in deep learning and machine learning. So if you see this feature f1 and feature f2, if they contain some overlap information, so that means maybe the generating process is somewhat similar. If the generating process is somewhat similar, so you will see that feature f1 also will have a little bit impact on feature f2. There is no necessity that they will always be independent. So usually we make an assumption that these two features are independent, but it is not always the case. Sometimes, because the generating process is similar, so there will be some dependency. Okay, generating process is similar, this f1 and f2 will have dependency. So why am I telling you this? Because it is a consequence. That is why you can reduce the dimensionality. That's why you can reduce dimensionality. What's the meaning of that? So if you have heard about algorithm like PCA, TSNE, so in that, if you have, let's suppose, 200 features, but your algorithm is now becoming very computationally expensive, you are thinking, can I now maybe reduce some features? You don't just reduce the features like I'll reduce this feature, I'll just remove the feature, I'll remove this feature, I'll reduce from let's suppose 200 to 50 features. But if you use this PCA, it uses mathematical principles in which it takes combination of these things. It takes some combination of all the features and reduce it to some fewer number of features. Okay, how does it do it? Because here the assumption is that these features are dependent. So what's the meaning of dependence? That is generating process is similar. So if the generating process is similar, that means if this feature f1 is there, if this f2 is there, if let's say f100, f200 is there, somehow I can construct a new feature which takes a combination of other features, and that means that I can have the features which have somehow the information that is contained by other features as well. So because of this independence, because of the dependence, I am able to reduce dimensionality. I am able to reduce dimensionality. Maybe I'll lose some information, but I'm sure that I'll not lose 100% information. If I had, let's suppose, 200 features, so if I make independent assumption, that means each feature contains, let's suppose, 0.5% information. So each of the features contains 0.5% information. If they were independent, then it would have been impossible to reduce dimensions. Why? Because the more features you'll remove from it, that means, let's suppose if you removed 100 features, that means you would have removed 50% of the information from it. But because they are dependent, because these things are dependent, so we're in a position so that what we can do is we can maybe take one feature, because somehow its information is also encoded in some other features as well. So if we just remove some, let's say, 100 features, and we consider that these features are dependent, and it also it's subject to the condition that how much dependence is there. So you can just remove from 200 to, you can go to 100 features, and you will probably preserve 98% of the information. That usually is the case. Okay, because when you do feature engineering, and when you reduce these features, and then you reduce it from, let's suppose, 200 to even 5, 6, even 10 features, top 10 features, and then you will see these top 10 features, because these things were not completely independent and they were not identical also. Okay, so what happened, because as a consequence of that, you can reduce the number of features by still keeping the information intact. Not whole information, you will have still some lossy information. That's why it's called lossy compression. This thing is called lossy compression because there is some loss, but you are still compressing. You are compressing from 100 features to, let's suppose, 50 features, or 200 features to 10 features, something of that sort. And you are having some loss, but loss is 2%. Why can you do this? Because now the assumption is these features are not independent at all, or they are not identical also. They don't contain identical information also. So what they do is they contain different informations, and maybe some features also can be written as a combination of other features also, so we can remove those features. Okay, so this is because of the dependence or because of the independence as a consequence, because independence is the same concept, just one is complement the other. Okay, that's how you can think about these things. And one more thing, let's suppose if now you are solving two different problems, so the one is from domain 1. Okay, the causing process is different. Okay, let's suppose weather causing, what are the features that affect the weather? So there will be some features which will be causing it, at least which will have some correlation with it. And then there will be domain 2. This domain 2 will have some other features, or it will have some other process which will cause these things. So these two things will be considered independent then. So now the problem was, if given we have a king, and one assumption was that always boys are predecessors, that is boys are made kings. So if in a family there are two children and one is a king, what is the probability the other sibling is a female? So the discussion we did is, so if you see, so we said the one way of thinking at this is, that is an instinctive thinking. So we'll assume that since there are only two biological options, male or female, the probability of king sibling being a girl must be 1/2. But because this reasoning fails to account the given information. So we had some information that was given to us, we did not account it. That's the problem with this. So we did not update our priors based on the evidence, because we now got an evidence, so we should somehow update our information based on the evidence. Okay, that's why we should resort to the conditional probability, not just to use the intuitive notion that is one child is a boy, then second child, because it's a biological phenomenon, it is 1/2 and 1/2, so I'll just go to 1/2. But because you had initial hypothesis, probability of a girl child, this is, let's suppose, 1/2. Now you have to say probability that one is boy, that is one is king, and other is girl, given that you have a boy. This is what probability gives you. It gives a notion of thinking. Okay, and once we did it, so I said the initial sample space should be girl boy, girl, and boy. So now if all of these are equally likely, okay, that's a pretty decent assumption to make. So all of these things will get 1/4 probability, 1/4, 1/4, 1/4, and 1/4. Now I am told that there is a king in the family, that means there is a boy in the family. So that means it just restricts me to only these three possibilities, and it removes one of the possibility. That's girl possibility is not possible now. Okay, now I have to reshuffle the possibility. I have to now tell me, okay, these are the possible things that can happen there. So what is the new probability now? Okay, the new probability should be 2/3. 2/3. Why? Because I have to renormalize it. It was initially 1/3. Each of these will be now. It was initially 1/4. Now once I renormalize the probability, it will be 1/3. This will be 1/3, and this will be 1/3. Now these two conditions are favorable to me. This girl boy and boy girl, because this boy should not be there, because I am asked that one of the other sibling should be a girl child. So that is 2/3. Now the lessons that I told you here. The first thing is, it depends on modeling. How do you model the problems? Okay, it depends on a lot on modeling. And modeling depends on the assumptions. Okay, when you see a probabilistic phenomenon, you have to model it somehow in order to land the result. Okay, in order to model that things, you should know the assumptions that you are making. Okay, so here I connected this with why are there a lot of models that we use in generative AI while generating new samples. So many of these are probabilistic models. So why are there different models? So what they assume is the assumptions are different, and they model the process differently. Okay, so different generative AI models, okay, they model the probabilistic phenomenon differently. Probabilistic differently. Okay, so this should be your lesson from this problem, that once you see a problem, you should know how to model it, and there is no wrong way of modeling. So given the scenario and given the assumptions, that's why the problem lies within the English. The problem lies with this language, because this language is so open to interpretation. So once you are given some problem, once you are given a question, you can make any possible assumptions that fits the description. Okay, so once you make those assumptions, you will model the problem accordingly. Once you model, you land the result. So if your assumptions are right, or if your assumptions are quite logical or quite coherent, then probably you'll still get a model. So which model will be better will depend on how good its assumptions are. So if assumptions are very good and you are modeling your process based on that, you probably will have better results than others. Okay, and sometimes because we model a problem and we miss some assumptions, and this model performed really good, and maybe its assumptions were very strong, its assumptions were very good and very coherent. That might be one of the reasons, and we'll have to dig deeper. Okay, what is the assumption that this model is taking while we are modeling the problem? Okay, so usually what I said is GANs, they don't produce good outputs as produced by diffusion models. If you have to look into these things, why is it happening? So probably this diffusion models is modeling the problem pretty good. Or if you see variational autoencoders, even both of these things are modeling a problem, they are trying to come with a probability distribution. But maybe this diffusion model, when we say that it is performing way better, it has to either do with it is modeling the problem very good in a better fashion, that also suits the machine, that also suits how our machines are the computation. Okay, and maybe this problem is also there. Maybe GANs also model the problem really nicely, but the problem could have been with the machine itself. So how GANs are implemented, and they might assume something about computation. So when we do those things on the machines, so maybe they don't produce very good samples. So otherwise we had Boltzmann machines also before GANs. So they also are in parallel. They also almost work like in a similar fashion. But Boltzmann machines were unable to create good samples, but GANs were. So these are the lines where the understanding becomes very blurred, because now we have not understood the process fully. So once this idea of GANs was proposed, people are thinking it should fail miserably, but it was working unreasonably well. It was at least generating samples. Okay, when the GANs paper came by N. Goodfellow, and people were like, oh, it almost is like Boltzmann machines. Why are Boltzmann machines not working in this scenario, and why are the GANs working? And probably if you have to dig deeper into mathematics, you will see probably GANs is making some assumptions, and it is, once it is doing computations on your machine, those assumptions are feasible with your machine. Okay, similarly with the diffusion models. So here what I said is, so all these phenomena are basically modeling the same problem. Okay, but modeling differs. Maybe your assumptions are different, and some may also sort of support the computation that you currently have. Any questions still here? Let's move to the next topic. So next topic will be something called as conditional independence. Conditional independence. So if you see independence, so generally in independence we had two events. We said probability of, let's suppose, A and B. Okay, this is equal to probability of A multiplied by probability of B. This is what we wrote. So what is this conditional independence now? Now let's suppose we have some other event on which you condition these things. So I'm saying probability of A and B given C. So this is equal to probability of A given C, probability of A B given C. So from this I am saying that conditional probability, they behave like normal probabilities. Conditional probability and with the independence, they behave like normal probabilities. You can prove this mathematically also, but you can take my word for it. So this is what is called as conditional independence. This is conditional independence. Okay, so it basically means like if you have two events, so if you have two events A and B, and they are conditioned on C. Okay, in order to tell now that this is conditionally independent, so you should be able to, this definition should follow. This is by definition. Okay, that means happening of C gives no information to A and B about each other. Okay, if event C happened, no information is, still you can use the same things. Okay, if you have event A and you have event B. Okay, so when do we call these two things independent? We say that these two things are independent if happening of A does not give me any information about B, and the vice versa. Okay, if they are independent to each other. So now if some other event happened, if some C event happened, so we'll still say that this is conditionally independent. If this happening of C does not give me any information about happening of A and B, it does not give me any information that let's suppose now if A will happen, still it will not give me any information about B. If B will happen under the condition C already has happened, it will not give me any information about B will not give me about A will not give me about B under the condition that C has happened already. This is called as conditional independence. So can I assume that you understood conditional independence by definition? Now if you understood what is conditional independence, so now there are two problems which people usually confuse. So there are two ways to go about this. Does independence mean conditional independence? So question 1, does independence mean conditional independence? And vice versa. Question 2 is, does conditional independence imply, I should say imply independence? So for the first question I am saying if two events are independent, okay, does it mean that if I am conditioning on third event, will it always be independent? Or, and second question is, if there is conditional independence and something is conditioned and the events are still independent, okay, we have two events A and B, and if they're conditioned on C, these events are conditioned that they're independent, and can I assume that these events will be still independent even if I remove that condition? So what do you think the answer to these questions is? Intuitively, what do you think if you have understood independence? So these are the two questions. So let's now put this question one mathematically. So does independence imply conditional independence? So let's suppose by this what I meant. So by this I meant, let's suppose if we have event A and B, and if they are independent, so mathematically it means that probability of A and B, probability of these two happening together, is equal to probability of A multiply probability of B. If this is the case, so does it mean conditional independence? So does this imply that probability of A and B given some C happened is equal to probability of A given C multiplied by probability of B given C? So the answer was no, this is not necessary. Okay, if we have something, we have two events A and B, and if we condition them on something, let's suppose, and maybe it might happen that the conditioning event made the other events dependent. Okay, I showed this by a Venn diagram like this, so we'll show it here. So here we have, let's suppose, event A and we have event B like this. So this is event A and this is event B. If some event happened like this, if this is event C, okay, initially A and B could have been independent if these two initially were independent. Now after C happened, so I have to restrict my sample space to these two positions. Now this C happened. Now you can clearly see that happening of C made these two events dependent. Okay, so this is not always the case. Okay, you can prove it also algebraically, mathematically, but this is not the concern. You should rather learn intuition first, and then whenever you get time, and you should try to prove them mathematically also. So again, the second thing was, if we have this simply, if let's suppose something is, if something is conditionally dependent, something is conditionally independent, does it imply that it should be also independent unconditionally? Okay, here I also said the answer is no. Okay, and the example we did is, let's suppose you have an alarm which is caused by two things. Let's suppose this is caused by fire and this is caused by, let's say, cooking or something. Okay, something of this sort. So now if we have conditional independence on both of these things, so what will happen is, so maybe conditionally they were independent. So probability of, let's suppose, alarm given it is fire, okay, was something, and probability of alarm given that it is, I should rather write the reverse of this, probability of fire given the alarm and probability of cooking given the alarm. So they were totally independent. Okay, they were independent conditionally. If you see it, like, you can make conditional independent. So once something happened, let's suppose once you make this conditioning thing, so does it mean independence? No. Now it will now give the additional information out. So these are the two examples, but you should try to also prove them mathematically. Okay, and you should try to come up with different answers. So the homework for you people is to come up with more examples. More examples that should be from the real world. Okay, so that where these two things do not imply each other. That is, does independence imply to conditional independence? No. And does conditional independence imply to independence? This is also false. Okay, so initially people sometimes feel that this should be true. Why? Because conditional independence seems like it is a more powerful independence, because it is conditionally independent, so it should be unconditionally also independent. So it is not the case. Okay, usually people get this one right directly. They say that it's independent when we condition. So usually this is not the case that it will always follow that it will always remain independent. But usually people get it wrong over here. Okay, so you should now try to reason it mathematically first, build an intuition around it by coming up with more examples, and then try to reason it mathematically and come up with the mathematical proofs. Let's now move on to the next topic, and probably the last topic of this conditional conditioning and independence. Then we'll move on to the random variables. Okay, the last topic which I felt is important to understand is this. So let's suppose now you have, if you have independence, let's suppose we'll the topic title would be pairwise independence versus full independence. Pairwise independence versus full independence. So what is the meaning of this? Okay, here I'll also leave you, you'll have to come with examples. There are a lot of examples written in the books. So when I yesterday discussed about conditioning, about independence of three events, I said probability of A and B and C. If this is equal to probability of A multiplied by probability of B multiplied by probability of C, I said this is not enough. So this thing is not enough. Okay, for the independence. But what you should do is you should also come up with pairwise independence. C and A, something of this sort. So you should also come up with pairwise independence. The probability of B and C is equal to this. Probability of C and A is probability of C multiplied probability of A. So here you can also prove that this does not imply this. So if you have pairwise independence, this does not mean that you will have these things. So you can come with examples, come with the numbers also. Okay, so you can see Ross and Schill, there are numbers here. So I'll give you a coin example. I'll not solve the full example, but I'll give you the coin example. So here the question is, if two things are pairwise independent, okay, if there are these things which are pairwise independent, they are pairwise independent. Okay, it does not imply this. It does not. You have to explicitly prove this in order to say that this is independent. Okay, so pairwise independence does not imply to the full independence, does not imply to this independence. Okay, this is pairwise independence, and let's suppose this is 3 event independence, only one condition. So if you have pairwise independence, this does not mean this. That's why I said in order to prove that these 3 events are independent, you should prove all of these things. Okay, because these 2 things do not imply each other. Okay, with this I'll close the independence and conditional probability over here, but I have left a lot of things unsolved and a lot of things unsettled. For that, I assume you will do a lot of examples on your own. You will think while watching these videos. Whenever I have a pause, we had a discussion over there, so you'll just pause over there and think about the discussion that we had on that time. Okay, and wherever I have left things unsolved, unsettled, so you should think on those terms and you should come up with your own intuitions and maybe have a good discussion with other people as well, so as to come up with right notions of probability. And from the next lecture onwards, so we will go to the random variables.